Hey, yo, what's up, guys? Baby Bear 4812 coming at you one more time with a tricky problem today, but a really cool one. It's problem 1274, number of ships in a rectangle. I think it's from a relatively recent contest. So it seems that only Bloomberg is asking it these days, but I got I got a request to answer this question in the comment section below. And so here we are. If you have any others you'd like me to answer, feel free to drop them down below. And yeah, without further ado, let's look into this one because I think this is a really tricky one. I do. So we're told that it's an interactive problem, meaning we're given some sort of API behind the scenes that we're gonna work with, and we'll get into the details there. But the question says the following: it says that each ship is located at an integer point on the sea represented by a Cartesian plane, and each integer point may contain at most one ship. So, for instance, we got a Cartesian plane here, and we can pretend that each one of these blue blips in this red rectangle is a ship. We have a function c.hasShips, which takes top right and bottom left. So it takes 2 points as arguments and returns true if there is at least one ship in the rectangle represented by the 2 points, including on the boundary. So if we're given top right and bottom left, let's say we're given this point down here, so or rather, I guess bottom left would be 0, 0, and top right would be 4, 4. This function, if we called c.hasShips with these 2 points, would return true, and true tells us that there is at least one ship within the rectangle formed, or the rectangle that exists within these boundaries or these lines, including on the actual boundary. And so we're let me see where I leave off here. Given 2 points, the top right and bottom left corners of a rectangle, we need to return the number of ships present in that rectangle. Okay, it is guaranteed that there are at most 10 ships in the rectangle, and submission. So this, first off, two kind of key pieces of information. One is there at most 10 ships in this rectangle. We'll talk about why that's important. Submissions making more than 400 calls to hasShips will be judged wrong answer. Also, any solution to attempt to circumvent the judge will result in disqualification. Okay, fine. So we get this example, and here our input, I guess our top right is 4, 4, as we said right here, and bottom left is 0, 0, and we would return 3 in our final output because there are 1, 2, 3 ships that exist within these boundaries. A couple other constraints we get, which are also important. We say on the input, ships is only given to initialize the map internally. We must solve the problem blindfolded, meaning that we need to find the answer given the hasShips API without knowing the ship's position. So we're not given the positions. We are told, and this is going to be important as well, is that the maximum size rectangle we can have is 1,000 by 1,000, or maybe 1,001 by 1,001. But for simplicity, I'll say 1,000 by 1,000, where the top right is not equal to the bottom left. So presumably we'll get some legitimate rectangle. All right, and let's take a look. So I've kind of left these comments here because they are important. They're pertinent to how we're going to implement this. We're told that the C's API interface is given. We don't need to implement it. We don't need to speculate about how it works. So it just works. All right. We're told that C is a class that creates an instance of an object, and it has a property, a function called hasShips. And like we said, hasShips will tell us whether or not the C within the boundary of these 2 points has any ships or not. Finally, just to kind of up the ante a bit, point is another type of object. Okay? So we have a class point which instantiates an object with 2 parameters. Those parameters are x and y. Namely, they'll be equivalent to the x and y coordinate of a given point. So instead of just using integers as points, we have an object type point. All right, so there's kind of a lot to unpack here. I know the introduction is running a bit long, but I want to make sure that we really get it before we dive into how we're going to solve it. Let's talk about how we would do this in a brute force way first, before we kind of do anything else. This makes it tricky. The fact that we can't make more than 400 calls to hasShips. Why does that make it tricky? Well, I'd argue the following. If I know that I've got some rectangle up to size 1,000 by 1,000, that means we've got, I guess, an area of 1,000,000, right? If we've got 1,000 by 1,000, our area is 1,000,000. And so there are kind of 1,000 dots, or 1,000 integer points by 1,000 more integer points, each of which may or may not contain a ship. So theoretically speaking, I could just say, well, from bottom left to top right, check every single coordinate one by one and check the hasShips function for each point one at a time. And every time it returns true, since I'm looking at only one single point, that means there's one ship in that point that I'm checking, and just do a sum every time I find a ship at any given point. That would be a really kind of simple solution. It would be, I guess, quadratic time, where it would be n by m, so number of rows by number of columns. But to make that harder, so like brute force isn't going to work here because we're capped to 400 calls. Okay? So we're going to need to get more clever about how we do this. This is kind of like one by one, linear walkthrough isn't going to cut it. So then we got to think to ourselves, okay, if just a standard linear walkthrough isn't going to do it, how do we do better than linear? Usually when we have this question, the way that we can do better than linear is logarithmic. And that typically entails, in almost all scenarios, some sort of divide and conquer type approach. All right, in some capacity, it'll be like a divide and conquer. And so let's think about how we actually want to divide and conquer this thing. Let's imagine that I've got some grid here, and it doesn't really matter what size this is. This is our top right point. This is our bottom left point, excuse me. So we're given, maybe I'm trying to draw a perforated line here. Maybe I've got something. This is my point, my bottom left point, and it's bottom left point x and bottom left point y. Those are kind of my two coordinates, if you will, of this object. Remember, it's a point object. And this is top right dot x and top right dot y. So again, we said, how do I can't really walk through this way and just do a quadratic walkthrough, because anything above a 20 by 20 will have more than 400 calls, and it's not going to fly. So we need to figure out how to divide and conquer this thing. Let's think about this. So what I said was, what if we reduce the size of our search to the smallest possible rectangle, which would be a dot. Technically, I know like mathematicians don't yell at me. I understand like a dot, a singularity is not a rectangle, but for the purpose of this explanation, like if I just checked one plot right here, like I said, if it returns true, I know I have one ship. Otherwise, I don't have any ships. If we were to do a hash ship search on this, we could, if there are 6 ships in this thing in total, it would return true. It wouldn't return 6. So this doesn't help me. So dividing down to each individual point is dividing way too far, because I can't do that many checks. Having a broad kind of check on just the entire rectangle in and of itself doesn't help me, because all I get is a true. I don't get a return of a number of how many ships there are here. So that means that I need to divide into a unit that's greater than just an individual singularity, but smaller than the whole rectangle in and of itself. And so how do we actually decide how we're going to divvy this up? So you may think to yourself, like, maybe I can split it in half. And maybe if we split it in half, we'd say, well, if I split it in half, I can call this half, and I can call this half separately. And now all of a sudden, it's like, well, maybe one of them has ships and the other doesn't. So we can kind of focus on that one. So almost akin to a binary search, if you will, kind of. But you can then kind of rightfully ask the question, what if I divide it into 4s? Right? What if I divide it into 4s and I said each quadrant I'm going to search into, and if any of those quadrants has a ship, well, I'm going to search further. I'm going to divide this one into 4 pieces, and so on and so forth. And so I think the tricky part in answering this question is figuring out actually how to split this thing. It turns out that the correct answer will be to split it in quadrants. So we want to figure out and say, if this is my general rectangle, and in this rectangle we can determine does contain a ship, then if it contains a ship, I want to figure out which part of it is going to contain that ship and only dive further into each of those parts. If I check these parameters over here, and we're going to talk about how we find these coordinates, but if I was to then search in this rectangle here and say there's no ship here, okay, cool, I've ruled this out. I'm not going to find any ships here. Maybe this one over here does contain a ship. So I'll say, okay, let me search this one down further. I'm going to now divide this one into 4s. And I think I've got the answer for why 4 will work. And bear with me, I'll get to it in just a second. And same thing, kind of by process of elimination, we can do a recursive jump down further into each of these rectangles, or these quadrants rather, to actually figure out the total count of how many ships we're going to get, so that the furthest we can ever drill down to is going to be to singularity. If I drill down to singularity and I'm returned a true, then that means there's one ship there. And then I can kind of take that back upwards, or I guess back down my call stack and say, okay, I found exactly 1 unit here. Notice that I still need to drill down to singularity, excuse me. I need to drill down to singularity to determine whether or not there is 1 ship or there is 0 ships, right? Or rather, I don't need the singularity to determine if there are 0 ships, but I need to get down to singularity if there's 1 ship. I can't tell how many there are if I've got this large rectangle and I return true on has ships. So we do this drilling down. So we ultimately get there, but as I said near the start of the video, I can't do this for every single singularity along the way. There will be way more than 400 for any inputs greater than 20 by 20. So why is it that this rectangular shape actually works? I don't have like the fully thought out, complete mathematical justification for this, but if we have our maximum shape is about a million, we said, right? So if we have a 1,000 by 1,000, 1,000 by 1,000 shape, how many times can I divide this into quadrants? So I can divide this into 4 quadrants, and then once I have those, I can divide it into another 4 sets of quadrants. So I'd have 16 quadrants, and then I'd kind of have, or they're not quadrants anymore, they're 16ths. Then I can divide once again into 64ths. And so on and so forth. And I think to kind of answer this question, we need to understand how many times can I divide a million by 4 to get down to singularity at most. The answer to that question is kind of like saying, well, 4 to the power of some x is going to equal 1 million. Another way to answer that is saying, let's take log base 4 of 1 million. So I'm going to use shorthand here. Very nicely, if we, and I'll just so you guys can kind of see what I'm doing here. Log of a million is 10. If we were to divide that by the log of 4, we get just about 10. Why is 10 important here? We're told there are at least 10 ships, right? And so I believe that's where all those numbers kind of come together. I'm not really sure where the 400 comes from, if I'm being completely honest with you guys. But this is why this quadrant breakup will work and not go over the total number of calls and kind of be within the parameters of how many calls we're allowed to make and how many ships there are in here. And so really to kind of summa summarum, to pull this all back together, to answer this, I need to say that if I've got a rectangle here, and it's a non-singularity rectangle, and it has ships inside of it, I need to break it into quadrants. And each of these quadrants will then need to be broken down into more quadrants if it contains a ship. If it doesn't, cool, we're not going to do anything with this. We're going to add the sum of all these recursive calls together. So for every quadrant, I'm going to have 4 potential recursive calls. And we'll talk about what the terminal condition is when we do the actual code. It won't be complicated. And this is basically how we're going to break this down. To actually find and divvy this up, this part I do want to kind of cover, and I've jotted my notes down here as always to make sure that I don't get anything wrong. We're going to need to determine if I'm kind of given a rectangle here, and I'm given, again, so I'll call this kind of bottom left x, bottom left y, and I'll call this top right x, top right y. This is how I'm going to want to divide it. I'm going to have kind of these integer quadrants that look as follows. So the space is kind of in between. It'll all be covered since we're working with all integers, so not to worry. I'm putting a bit of space there so it's visually a bit nicer. So how are we going to do this? When I get to my top left quadrant over here, I'm going to need to use some sort of midpoint x. So some sort of midpoint x, the midpoint between, this midpoint over here. Let me make sure I got this. Sorry, I'm going to want to use, take this back. So the implementation, by the way, let me just one thing that's really complicated, I find really confusing about this implementation, and maybe this is just me, but the fact that you need to call the top right corner and then the bottom left, for some reason in my head, I'm always tempted to put the bottom left and then the top right, just I don't, for whatever reason, for me, logically, it makes more sense to call the API that way, but it's not in my hands. So if you're making a mistake, if you already have this logic, but you're making a mistake in your code, double check that, because that might be where you've been going wrong. Anyways, this point over here will have the same coordinate as the bottom left x point, and it'll have some midpoint, we'll call it y plus 1. So imagine that we're going to have some sort of midpoint here. This midpoint would be like a midpoint of y. So this is going to be like a midpoint of x, and this will be a midpoint of x, so between these two, right? So x, this way we're going to have a midpoint. We'll call this midpoint x, and we'll call this over here midpoint of x plus 1, All right, so to kind of divide to check both sides of the midpoint. And then maybe instead of doing all these coordinates individually, I'll kind of say the following. I'll say this will be like a midpoint y, right? So in the actual height, and this will be a midpoint of y plus 1. I've now got coordinates here for each one of these. I've got my midpoint x and y's. I've got my y coordinates for my bottom left and my top right point, right? So these are given when I actually make the call. So are these x's. And so now all I've got to do is to calculate to calculate the midpoint of the x's and the y's, and then make the calls on these following points. So these points right over here, these two together, will make up the top left quadrant of the split that I want to make. These two will make up the top right quadrant. These two will make up the bottom right quadrant, and these two will make up the bottom left quadrant. And so we'll refer back to this diagram when we're actually typing in the code, but really, like, this is a pretty simple kind of, late middle school, early high school just geometric calculation, just to calculate, where we kind of split the rectangles up. So there's not actually much to it. The code will be simple, and it's just based on this idea of splitting it 4 times. I just think that coming up with that split isn't necessarily intuitive. So I hope the explanation kind of put a bit of intuition behind how we're going to approach it, and maybe at least shed a bit of insight into why it is that it's quadrants that we're breaking it down into. The time complexity here, I think it would get really tricky to calculate. I think it would be like a full math problem. So in an interview setting, nobody would be expected, it wouldn't really be expected of you to fully hash this thing out. But I think it would be reasonable to say that, look, I'm doing some sort of divide and conquer here, and I'm kind of cutting this down into logarithmic time. So you'd have some sort of maybe constant multiple of the logarithm of m by n, or x by y, and just the size of the grid. So that's roughly what the time complexity would be. And I guess with the space complexity, the only real space we're taking up would be the size of the call stack. Right, and so since we can't really make, I'm thinking about how many calls we can make, up to 400 calls on the API. So it's like I might hash this out later, as with some of my videos. I'll drop it down in the description if I have any corrections to make on the complexities. But I'd argue for space complexity, the only space we're going to be taking up is the actual recursive call stack. And so I believe overall that would most likely be constant, because we can only slice down so far into one recursive step. Like we saw, we can only kind of take 10 steps down, and we have to split down one quadrant before we start popping back up. And so that's why I'd argue that I believe it would be constant space. But again, if there are any corrections, I'll make sure to drop them in the description below. All right. So for those of you who've been watching my videos kind of long enough, you'll know that I like to write helper functions for recursive. So I'll call this one helper, and we'll figure out kind of what to do with it. Or maybe I'll call it find ships, just so it'll be a bit more descriptive. And what I want to do is I want to return the value of find ships when I call it using, I guess it would be the top right and the bottom left points that I'm given. Again, these two are objects. I think you can actually make this recursive call within this function as well. You probably don't even need to write a pointer. I'm just kind of doing this for consistency, for my own sake, because it's how I'm used to doing it. But you can feel free to kind of play around with it and actually figure out how to do it in just that one count ships method. And so what we're going to be passing in here is exactly like what we passed in here, which is the top right and the bottom left point objects. Now, here we're going to have some terminal conditions, and I'll put those in a bit. I want to get into the actual meat of the recursive relationship. I think that'll make a bit more sense. The first thing I want to see is whether or not I have any points in the rectangle that I pointed in, that I've called, excuse me. So if C dot has ships, so C is our C object, and has ships is the actual call API. So C dot has ships, and we need to pass into it top right and bottom left, right? We're told that's how the implementation works. Right over here, we pass in the top right point and the bottom left point. So actually, I should say, if it doesn't have, if it returns false, then what we want to do is we want to return 0 and say that there were no ships found here, so I got nothing to report on. Conversely, kind of in the terminal condition, our terminal condition will be if I've landed on a singularity, and that singularity has a ship, then return 1. Because we've kind of found one. Anyways, but before I get into that, like I said, I want to now figure out, okay, if I haven't returned here, that means that I do have ships in my quadrant. And so within this quadrant, within this rectangle. Now within this rectangle, I want to chop it up into quadrants. So I'm going to have some sort of like top left quadrant is equal to something. We're going to have a top right quadrant. We're going to have a bottom right quadrant, and we're going to have a bottom left quadrant. And again, we'll obviously calculate what these are. And after all this, what I'm going to want to do is return the sum of all these. So I'm going to want to return how many ships I have in my top left quadrant, plus in my top right quadrant, plus in my bottom right quadrant, plus in my bottom left quadrant. Maybe it's time that I move me out of the way. We've had enough. Plus bottom left quadrant. All right, so this is like the general shape of how we're going to tackle this thing. We said that we will need to be calculating these kind of midpoints here that we had down below. So to do that, what I'm going to do is I'm going to say I'll calculate my midpoint x to be equal to the bottom left dot x plus the top right dot x. So the 2 points that I'm given, I'm going to take both their x coordinates and I'm going to divide them by 2. Since these are capped to like 1,000, I'm not worried about integer overflow, so we're kind of safe to calculate the average this way by just adding the 2 numbers. Midpoint of y will be similar thing. We'll just take the left property again. So I'm doing this because point input here is an object. It's not an integer or a list or something like that. I'm going to take top right y, and I'm going to divide that by 2. Finally, then I'm going to create a point called mid, and that's going to equal to, it's going to be a point. So I'm going to call a point class here, and I'm going to initialize it with x and y. Strictly speaking, I don't think this is necessary. It's just when I did it, it made the code feel a lot cleaner, which is why I kind of wanted to put it in here. So now for the interesting part, which is where we actually need to make recursive calls on all of our quadrants. So for each of these, I'm going to want to call find ships, and I'm going to need to put in 2 coordinates into there. And half the battle here is actually just working out how to which coordinates to call exactly and how to calculate them. And this is where I kept making mistakes. Again, I think I kept swapping the top right and the bottom left because for me, it's just the opposite way made a lot more sense. But anyways, I'm done complaining about that. So what I want to do is I want to call the top left quadrant. So the top left quadrant we said is going to be this one right over here with this point here. Okay, so I'm going to need 2 points, and I don't know what those points are going to be yet, but this one over here in find ships is going to need to be top right. We're first doing top right and then bottom left. I'm doing it this way just so we can have a consistency with how the has ships was passed in. So top right and bottom left. Top right is over here. Top right is equal to, you can see this midpoint x here. So midpoint x, and it's equal to, and the y coordinate is equal to top right y. So midpoint x and top right y. So midpoint x was, we said mid dot x and then top right dot y. That represents this coordinate right over here that I'm going to call. That's my top right of this. It's my top right of my top left quadrant. Now I need to do the bottom left of this quadrant, and we can say that it's same as the x coordinate of the bottom left with midpoint of y plus 1. Okay, so bottom left x, that was bottom left dot x, and mid dot y plus 1. Okay, mid dot y, so it's y coordinate plus 1. Again, it's plus 1 because I'm kind of grabbing this upper half here of the midpoint, and then these ones are going to be just middle of one. They'll grab the lower part. This is the actual logic that I'm going to use for every single one of these quadrants. I'm going to look at, what's the composition of my top right point, my bottom left one, and put that in for every single quadrant. Once I do that, I'm done. That's really all that needs to be done to solve this problem. So the top right here in this quadrant is equal to actually to the original top right that we were passing. So that's convenient. So I'm going to call just top right over here, and then I'm going to go here and I'm going to acknowledge that this bottom left point here is equal to mid x plus 1 and mid y plus 1. That's the composition of this point. So we're going to create a new point that we're going to be calling in, and it'll be mid dot x plus 1 and mid dot y plus 1. All right, let me make sure I got that right. Looks good. Now down to our bottom right quadrant. In our bottom right quadrant, we've got down over here, this is, got to start with this top right point here. This has got the same x value as our top right dot x, right? They align this way. So we're gonna have a new point here, This in the top right section again, it's gonna be top right dot x is the x value they share. So top right dot x, and the y is middle y. So I'll say middle dot y. Now my next point, which is the bottom left corner, The x coordinate that I have is middle x plus 1. All right, so it's going to be mid.x plus 1. And the y coordinate is equal to the bottom left y, right? So see this bottom left y over here? They share the same y value. That was a horrendous attempt at a straight line. So bottom left dot y, right? And again, this exercise that I'm doing right here, guys, it's literally I'm just sitting down being like, all right, what's the composition of these coordinates? Like, where do they actually fall? At this point, this part is really closer to like a grade 9 math problem than a coding question per se. Finally, the last one that we're doing here is the bottom left quadrant, and its top right value is going to be middle of x, as you can see here, and middle of y, right? Middle of x, middle of y. So we're going to have point is going to be mid.x, mid.x, mid.y. And finally, its bottom left point is going to be, well, it's just going to be the same bottom left that we passed in. So it will be bottom left, that exact same point. The only thing I haven't done here is the terminal conditions. And so what I want to do is I'm going to do the following. I've kind of assumed we always get a rectangle when we pass these in. Ultimately, if we keep kind of dividing and finding these midpoints, we're going to get a crossover, like where, you know, if you're thinking binary search, like where left is greater than right kind of issue. So what we'll say is that if the top right dot x is less than the bottom left dot x, meaning we've kind of like, we almost have like an inverted rectangle, so the points are kind of opposite from where they should be, or if the same thing happens on y. So if top right dot y is less than bottom left dot y, then we want to return 0. So I've searched too far. I don't have a valid rectangle. Like, all right, there's nothing here. Just return 0. Otherwise, the one we're really interested in is there an actual, like, what if we get to singularity? So if top right dot x is equal to bottom left dot x, and top right dot y is equal to bottom left dot y, what does this mean? This means that the top right and bottom left points that I passed in are actually equal to each other. I'm looking at a singularity. I now want to check the singularity to see whether or not we can, like, we have a ship here. So what I could say is if C dot has ships of top right, bottom left, if it's true, then we're going to return 0. Otherwise, we can say, you know, otherwise return 1, something like this. I just kind of put this in like a more succinct way when I did it, and what I did, which I thought was a bit clever, I said return the integer value of whatever this returns. And the reason we can do that is because if it returns true, then the integer equivalent of true is 1. So we found 1 ship. Otherwise, if it's false, it returns 0. So we're just going to return 0. And that's how we get these two terminal conditions. So otherwise, if we have a valid like full rectangle, we go through all of this. Let me give this a quick run just to see if I made any mistakes here. I got invalid syntax. Line 31. Thought I was typing in English, not Python. Cool. Let's try to submit this, see if we get the test cases. There we go. Awesome. So as you can see, speed super good. Space is like, we can't really do anything about the space, but you know, we did what we had to. There's the code in its full glory. I think this, I haven't checked the time before I started. I think this video ran a bit long. So for those of you who've made it, I hope this was helpful. I thought that this problem kind of warranted a bit of extra explanation and just figuring out how to slice and dice this thing, because I thought it was really not intuitive, but I thought it was good, irrespective of its difficulty. As always, like, comment, share, subscribe, all that fun stuff. If you have any other questions, let me know in the comments down below. Happy to answer them like I did with this one. And as always, I'll see you guys in the next video. Peace.